So I guess it is 4:01. I will think I will start the talk. So Alex, are you ready?
Yeah, of course.
Okay. So first of all, welcome to the first CRM Applied Math seminar, the virtual one. Say we had to cancel many of them, and now today is the first one. So that's kind of a test. Hopefully, it's going to be successful. And we're lucky to have Alex Townsend, who was supposed to be our speaker, I guess, last month. So everything was arranged. And in fact, we decided the day before he was coming to McGill that he would not come. So that was really one of these talks that was pushed to the limit. But now we're happy that he's accepted to give a virtual talk. And well, he'll be our speaker. So let me introduce him a little bit. So he got his PhD in 2014 from, the face that you can see on the screen with Nick Trefethen. He did his PhD at Oxford, and then I guess he spent a couple of years at the MIT for a postdoc from 2014 to 2016. And since 2016, he's a tenure track at Cornell University, where he's right now. So that's in Ithaca. That's where he is geographically right now. So please, Alex, you're welcome to start your talk, and thanks for accepting.
Yeah, thank you very much for the kind introduction. It's good to give a talk. A lot of my talks I've been giving have just been cancelled, so it's really nice to at least see some other human faces, at least briefly. Okay, so today I'm going to talk about what's called the ultraspherical spectral method. It's a type of spectral method that uses so-called ultraspherical polynomials. So whenever you have a continuous problem, such as like a differential equation, you've got to discretize it somehow before you can implement that on a computer and run some of your numerical algorithms. So today I'm going to be discussing how we've been carefully discretizing functions as well as ordinary and differential equations so that we can develop some efficient, stable, and highly adaptive methods. So this is joint work with a selection of people, including more than this. These are the main characters, though. Daniel Fortunato, who's at Harvard, Nick Hale, who's at Stellenbosch, Sheehan Olver, who's at Imperial College London, Nick Trefethen, who's at Oxford, Grady Wright, who's at Boise State, and Heather Wilbur, who's at Cornell. Okay, and I have a cursor that's giant so that I can hopefully show you, point to some things. Okay, so I first wanted to introduce a whole selection of software that maybe 25 or so people have been working on since 2004. These are pieces of software written in MATLAB, Julia, and Python, respectively, that discretize and solve problems involving functions, and as well as differential equations. There's Chebyshev, which you may have heard of, which was the first one in this group of software systems that discretizes functions in 1 and 2D. Benham, who's joining us today, did a lot of work in 3D. It discretizes functions on the sphere, in the ball, on disks, and allows you to compute with those functions numerically. A Proxfund, which is very similar over here, and as well as Deldas, it's a computational astrophysics software primarily, but in addition to that allows you to work with functions, computing. So for example, integrating functions, evaluating functions, solving differential equations with different forcing terms, and so on. So these are built over three different I always think of these as three pillars to building these pieces of software. You need good algorithms, good ways to discretize. You need some way to do adaptivity, because what we're going to do with these pieces of software is hide the discretization away from you. And I'll get into what that means. So when we discretize a function, you're going to be working with that function, let's say in Chebyshev, without realizing that there's an underlying discretization at all. And every time you ask us to compute something, let's say compute an integral, we will deliver to you that integral to machine precision, but you don't, anywhere throughout that process, do you need to give us any more information than the integrand that you want to integrate. So this is what I've been meaning. So that's the HP adaptivity. And then we hide that away from the users by using encapsulation. So these are usually object-oriented programming techniques that just allow you to work with objects thinking that they're continuous objects like functions and differential operators. But behind the scenes, we're adaptively discretizing and applying our algorithms. So underneath all of these pieces of software, we discretize functions, differential operators, as well as sometimes geometry, which I'll get into. Okay, so let me get more specific about what exactly I mean. So the simplest setup you might have is I have a function f that I want to compute with, so evaluate or differentiate, find its roots, and so on. So here's this function. In these pieces of software, this function gets replaced by an expansion. This is a Chebyshev expansion. These TKs here are Chebyshev polynomials. So this right-hand side here is a polynomial of degree at most n. We do this replacement so that we can compute with f. So f could be any black box function. It could be nasty, it may not have a closed expression. It may involve lots of different things to evaluate f. But we're going to replace it by what is in the end a polynomial in the simplest case. So that when we go and do, if you ask us to integrate, we're actually going to integrate a polynomial instead of your black box function. Now we're going to replace it by a polynomial in a way that this approximation sign is accurate to machine precision. So we've effectively tricked your computer into thinking it's working with f, but actually it's going to be working with a polynomial, and your computer cannot see the difference because we're going to do this approximation up to machine precision. So here is an example. If I take a function like e to the x plus 10 minus e cos 40x, here are the coefficients that appear in this series, this Chebyshev series for this function. You can see that they're large, and then once k gets a certain size, they decay and they eventually plateau out at machine precision, 10 to the minus 16. So when I give, in this case, I gave Chebfun this function, it applied an algorithm to where it evaluated f at certain points and then computed these approximations to these coefficients, ck, and worked out that it needed around 60 terms, a 60-degree polynomial, to represent this function to machine precision on -1, 1. So then for the rest, then we're going to replace f by this polynomial of degree at most 60. And every time you ask us to work with this function, we will actually be working with this degree 60 polynomial instead. Now, this is the simplest setup, but in addition to this, we can have piecewise, we can have weighted spaces, different maps. So here is an example where I'm showing you the HP adaptivity that this piece of software has. So here I've called a function. It's made up of smooth pieces because of this apps. There's pieces that are smooth, so this is piecewise smooth, but it also has a blow up on the interval. It blows up at 0.2. And so Chebfun here has worked out all by itself without me telling it anything. It's worked out exactly where to break this function. So it's made up of piecewise smooth pieces. So these are the polynomial degrees that it uses on each interval down here. As well as figuring out a blow up. So it's figured out that at 0.2, the function blows up. And it blows up with an exponent of 1, like 1 over x at 0.2. And so that's what it's telling me here. So this piece of software has figured out all those things and then represented it by a piecewise polynomial. Okay. So once you've done all that, in the end, this function f is just what we think of as a Chebfun object. It's just a encapsulated object that houses piecewise smooth, piecewise polynomials. So if you call, for example, sum of f, or integrand, that does computes the integral, then it will just go along and apply, correctly integrate. This function is infinite, but for this function, it would just integrate it to nearly machine precision. Okay.
Alex?
Questions. Yes.
Yeah, so basically the polynomial that interpolates the function that blows up. So you mentioned before that, with the exponential of x plus 10 to the minus 9, it does it to machine precision.
Yes.
So what kind of algorithm or stopping criteria? Because now I can see that there's a polynomial of order 9.
Yeah.
And I mean, now the precision is measured. I mean, how do you get it?
How do you get this? Okay. So if you evaluate this, if you can imagine evaluating this logarithmically close to 0.2, and you plot that on a log-log plot, you would see a straight line, a blow-up, which is a straight line as you go into 0.2. By measuring that gradient of that line, we can predict with reasonably good accuracy the exponent by that gradient of that line. Once we have the type of singularity we have at 0.2, we can go back to the function f and try to replace it by x minus 0.2 times this whole function by x minus 0.2.
Okay, yes.
And now approximate the remaining thing by a polynomial.
Yes, makes sense.
Okay, and then once we have that, then we call this adaptive code to figure out how many points we need. And you can just imagine doing it on all the pieces.
Yes. Okay, great, thanks.
We also have a separate algorithm that figures out where to break the function up if we're not getting convergence. So these actual breakpoints to get 13 are actually solved for to machine precision. You have to be extremely accurate to make sure these polynomial degrees are small. So there's a lot going on here, but this takes less than a millisecond. It's really fast. Lots of dirty engineering tricks, I think we should say.
So I have a question from Miguel Ayala. He's asking, why is the total length important?
I mean, that's just basically a count of the total degrees of freedom, or the total number of parameters that have been used to discretize this function. So in some sense, it's the total complexity of our approximate.
Okay.
Yeah.
Thanks.
Okay. So, okay, it's not just 1D. We want you to have this 1D thing. That was back in 2006. We had things that looked like that. By now, 10 years later, we have a whole bunch of different things that we can do. So we can do 2D versions of this, things on spheres, things on hemispheres, vector calculus in the ball. This is on a 3D ball. We got bivariate root finding problems. I just wanted to give you a highlight to make sure you don't realize this is not just 1D code anymore. This is code that can solve lots of different problems on simple geometries. So instead of simple for grants, we always say scientific geometries to make it sound better. Okay. Daedalus has taken it maybe a little bit further and gone high performance computing. So here is actually a simulation. It's a 3D simulation of heat convective waves that from a heating plate on the bottom. It's a vertical slice through this. And here you're seeing the heat, the temperature map over time. And so they're using the same, very similar techniques here to solve a PDE. Here is, if I stop this, and here is the Navier-Stokes equation on the disk. So here, this is basically like a Petri dish, and I've set off two vortices, one turning clockwise and one turning anti-clockwise. These are dipoles, but then because of the difference, they end up hitting this circular wall, bouncing off, and this is a fluid flow problem. Okay, so this is a nonlinear PDE that I'm solving over time. Each time slice, this thing is being discretized by Chebyshev. There's Chebyshev polynomials behind this, discretizing this solution. Okay, so you can just see the vortices spreading as you might expect milk spreading in a coffee cup. We don't just solve, like maybe you consider these to be toy PDEs. Here is a PDE called an active fluid PDE, which was a collaboration with people at MIT. This is simulating bacteria swarming inside a soccer ball, essentially. And here, these are the vortices that these bacteria are causing on a fluid. And so they're interested in this to build turbines, to extract energy from bacteria. But this is a difficult PDE in a simple geometry. And here this is some people looking at droplet dancing on a petri on a table, and the water tension. This is just a water drop dancing around, and they're interested to know, how to make this dancing happen, what frequencies to drive the table. So they're basically playing music to a drop and watching how it dances. Okay, so these are the kind of stuff that we're getting into nowadays. So,
and one question. So all you mentioned that Navier-Stokes was done using Chebyshev. So all of the others as well.
So yeah. So I have extra slides at the end to talk about exactly how this is discretized. But yeah. So this is so in the radial direction here. This is an interval. Let's say this is an interval, right? On the diameter.
Mm-hmm.
You could regard that diameter as being an interval between -1 and 1. So in that direction, that's a non-periodic function looking like I had before. And so I could approximate that by a Chebyshev series. But then in the angular direction around this way, if you do it right, you can get it to be a periodic function. It just repeats itself. And in that direction, you would use Fourier. So, and then in the sphere, in the ball, it's 2 Chebyshev and 1 Fourier. So it's a bit more complicated, and this is also Chebyshev and Fourier.
Okay.
So in the end, it's a mixture of those techniques. So anyway, we're going to get into it. So the story I'm going to tell about how we were slowly working up to those more complicated examples is I'm going to start in 1D and try to say how carefully we had to discretize differential equations, how carefully we had to do the HP adaptivity, so that we could get robust calculations. So, okay. Spectral methods are discretization methods for differential equations that have a really bad reputation. They come from the high order limit of finite differences. So here I have just a simple ODE, and I've discretized it, let's say on an equally spaced mesh, and I've thrown down my second order central finite difference scheme. And I'll get myself, in this setup, a tridiagonal matrix that would approximate this solution. Of course, I don't know how to, maybe I just have to play, but then I lose my, maybe I have to play here. Of course, I could go up order to the 4th order. So that would give me a bigger stencil, increase the bandwidth of my matrix, but would give me a better approximation to the ODE. Of course, if I take this to the limit, I have myself a spectrally accurate method. This is where, for the given discretization size n, I take a full stencil. So the stencil just involves every single value at every point. And this is called a spectral collocation method. It's the high order limit of finite differences. Now, this is the original spectral methods. They have spectral accuracy, is what we call them. And these methods don't work out so well when you have large discretization sizes. So why is that? Because they result in dense and ill-conditioned matrices. So here on the left, I have a plot of the computational cost it would take to solve a linear system. Theoretically, it's just Gaussian elimination on a dense matrix. So it's n cubed. Because of BLAST3, for some reason, my computer always gets n to the 2.5. On the right here, I have, I'm showing you the problems that could be caused by the ill conditioning of collocation. So here I have great spectral convergence initially. And then as I grow n more and more and just like over-resolve the problem, actually my error gets worse. My error gets worse because the matrices I'm solving are more ill-conditioned, and therefore the linear systems are sensitive to perturbations. So you can imagine this causing quite a bit of trouble in more complicated examples if I wanted to find out what n do I need to resolve my solution. Because if I over-resolve, I actually end up with a worse accuracy than if I under-resolve sometimes. So dense and ill-conditioned matrices. But at least in the periodic case, most of us will know a method that is spectrally accurate, but doesn't have any of those problems, and that's called the Fourier spectral method. So if I gave you a periodic problem where you could throw down a Fourier series as an ansatz for the solution, you'd be able to write down what I've written down on the left here, which is a discretization of this ODE using Fourier. And because, if I differentiate e to the ik theta, I just get ik. Here you can see it's just a diagonal matrix with one row, and that row is implementing the boundary condition, the constraint u pi equals 0. So a Fourier spectral method, at least in 1D, typically will give me bounded matrices with a dense row or rows corresponding to constraints on the solution. Now, these matrices are nothing like the spectral methods that we came from doing the finite difference and taking it high order. They're well conditioned. In fact, here I'm just plotting the condition number for different n. Condition number is bounded by 4. You can see that here. I mean, everything in this left-hand side on this diagonal, up to a column scaling, it's just a diagonal. It's the identity matrix, right? So if I take that diagonal scaling out, it's perfectly well conditioned. So back in 2013, we were sat around scratching our head trying to think of what is the Chebyshev version of this, because this looks great. This is exactly what we want. And because Chebyshev are the non-periodic analog of Fourier, you can just see that from their derivation. So you hear, like, on the left, I've got e to the ik theta. On the right, I've got cos k arc cosine x. That's a polynomial on the right. These two are very well connected. One is the non-periodic analog of the other. Now, the reason that Fourier spectral methods give you sparse matrices is because of this very simple fact that if I differentiate a Fourier mode, I get the Fourier mode back up to a constant. Now, one of the issues with Chebyshev is the reason you don't typically get sparse differentiation matrices, sparse discretizations of ODEs, is because when I differentiate a Chebyshev, I don't get just a Chebyshev polynomial back with a multiple. I get a whole series of linear combinations of lower degree Chebyshev polynomials. However, when you differentiate a Chebyshev polynomial, it's still a Chebyshev polynomial, right? It's still, when you differentiate a Chebyshev polynomial, it's still a polynomial. It's actually called a Chebyshev polynomial of the second kind, which is here. This horrible formula is still a polynomial, obviously, because I just differentiate a polynomial. So that polynomial has a name, and I'm going to call it C. I'm going to just denote it by C1. So we have ourselves a method here, or a way to think about derivatives that could lead to sparse matrices. So here I have, if I differentiate Chebyshev polynomial one time, I get a multiple of some other polynomial. If I do it twice, I'm going to get another polynomial, and it's some multiple of that. 3 times it's another polynomial, 4 times it's another polynomial. So instead of the Fourier spectral method, where I could always work with e to the ik theta, and I never had to worry about any other basis, if I'm thinking about in the non-periodic setting for Chebyshev, provided I keep this hierarchy of bases, T, and then C1, then C2, then C3, then C4, keeping these sparse relationships between derivatives of Chebyshev, then I could use that to come up with a sparse spectral method. Okay. So that's the idea. Now you have to sit down for a few days figuring out how to put all those pieces together once you know these sparse recurrences for high order derivatives. Okay, so right here I'm just like putting down some recurrence relations that tell you how Chebyshev polynomials relate to the other Chebyshev polynomials, and you need to know how the Chebyshev polynomials relate to these other C's, these other C lambda bases. But the idea is now every time we differentiate, instead of staying in the same basis, we will both differentiate and change basis at the same time. And that will give us sparse matrices that represent derivatives. And these matrices here that are called C's are known as ultraspherical polynomials. Hence why this method we're generating is called ultraspherical spectral method. Okay, so so here is a simple example, and I'm going to, d over dx is now going to both do a derivative plus change basis. Okay, in that setup, I've got a linear system here, which is still banded, plus one row, which is dense. It's exactly like the Fourier spectral method. Even so, if I look at the condition number of these matrices scaled appropriately, it's bounded by a constant. And actually, this method is very similar in flavor to a few other methods like Petrov-Galerkin methods, which you may have known, integral reformulation, Chebyshev's method going all the way back to the 1920s, and so on. But here this method feels exactly like a Fourier method. So that's the real difference. It's been motivated and feels exactly like a Fourier method. Okay, are there any questions about this?
Hi, Alex. I have a question. Can you hear me?
I just realized, sorry, I just realized I know you. So how are you doing?
Yeah. Yeah. Yeah, so I was wondering about the condition number. Like it's still bounded, but it's kind of a bit larger than Fourier. Is this kind of more pronounced in higher dimensions? So kind of
yeah, it's a good question. So in the 1D situation, we have a theorem which says the condition number can always be bounded by a constant independent of n, the discretization size. In 2 and 3D, that's a completely open question. We don't know. We observe that it's often doesn't grow with n, but we don't actually know how it behaves. And we have no sense of what that asymptotes to. If it's better or worse than a Fourier spectral method, we don't know. So there's some theoretical questions there that we just, we just don't know. All we know is it's bounded by a constant independent of n in the 1D situation. And then we observe that throughout many other problems in 2 and 3 dimensions. Okay. So, so once you've got this way of discretizing, then you need to make it adaptive by selecting the n for the user, and then you encapsulate it. So we have our algorithm, right? And then here you can see I've encapsulated it. Here you just tell me the ODE, tell me nothing more, tell me the ODE and the boundary conditions. And this backslash here, which is an overload of the backslash in MATLAB for solving a linear system, went and figured out the discretization size for me to resolve the solution to what it thinks is machine precision. And I call this the bucket equation because the solution looks like a bucket. But you can see I've got 21,000. N had to be 21,000 to accurately represent that sharp boundary layer. And so underneath, I was solving 21,000 by 21,000 linear systems, which you cannot get to from a spectral collocation method. Or you can go like really high order. So in spectral collocation, the higher order you go, the more ill conditioning you have. So here I'm doing it in a different software system. And still I'm getting 14 digits, even though I have a 10th order ODE, which is extremely high. Okay. So the idea, change basis when you differentiate, and you can keep your matrices sparse, even though they're spectrally accurate. And they're also well conditioned. Okay. So that's how we do 1D. That's how we discretize 1D ODEs. Now I want to start talking about how you might do this in 2D on simple geometries, let's say. So an idea that I just really like, it's just an idea. It just is, if I can do certain 1D computations, you can instantly start doing 2 and 3D computations as provided you're in tensor product spaces. So for example, if you can work with vectors you can instantly do matrices, provided you write down, every time you see a matrix, you write down its low rank representation. Then you can actually store a matrix as just a collection of vectors. And actually, this is how a computer stores a matrix, right? Even for functions, this works. Instead of thinking of a function depending on x and y, you can separate out the variables and think of it as a sum of rank 1 functions, where a rank 1 function is a function that only depends on a function of x times a function of y. And so here you can see I've written down a function that's of rank at most r. Okay, and then you could imagine trying to figure out how to best approximate a given function by a rank r function. And actually people knew about how to do that problem before they knew how to do it with matrices, which I just like as a historical fact. That the Urquhart and Young paper, which said the SVD is really good, use it for matrices, already existed in 1907 for the more complicated situation of functions. We also do it for partial differential equations. So given a partial differential equation that depends on 2 variables, we actually write it as a sum of what we call splitting rank 1 PDEs. And so you can write every single PDE as a sum of ODEs, essentially. And then if we know how to discretize ODEs, which we already do, we can discretize PDEs, provided that they have this tensor structure. So let me show you. So, okay, this is how we build up to 2D. So here I've just given myself what's called the gravity Helmholtz equation, but it's the Laplacian of u plus, okay, 10,000 y squared u. You can see I've got encapsulated code here. So this piece of code figures out everything. What is it figuring out? It figures out the low rank representation for the operator. So here on the left, I've got uxx, uyy plus 10,000 y squared u. It figures out that it can write it as what's called a splitting rank 2 PDE. So here, and these straight Ds are on purpose. You can think about this PDE here as the following, right? Differentiate twice in X, and then on the Y side, don't do anything. So that's my discretization, or my thinking for what UX is. It's differentiating X twice, don't do anything in Y. That's the first term. And then this second term here, you can see captures the last two terms. It says differentiating Y twice plus 10,000 Y squared and do nothing in X. So here in this simple case, you can see that this PDE can be thought of as rank 2. Now we know how to discretize 1D things because we already learned that with the ultraspherical spectral method. So now we can go along and discretize each of these 1D ODEs using the ultraspherical spectral method, and we'll have ourselves a 2D ultraspherical spectral method. So that's what's happening here. Okay, to do encapsulation, I have to first read off what the PDE actually is. That's actually relatively difficult sometimes. Then you have to figure out the low rank representation, which we can do adaptively. And then you have to play with the discretization size to get it to be accurate. So, but the main idea here is 2D is actually easy, provided you can write down the PDE in low rank form. Okay. So, once you've got this problem, right? Once you decide on a discretization size, you then got to worry about like how to solve all these things. And we actually send this off to a whole bunch of different solvers depending on the structures that we see. So a bit like backslash does in MATLAB for a linear system. If it sees you have a sparse matrix, it will send it to UNVPAC. If it sees you have a dense matrix, it will send you off to LAPAC, and everything in between. So banded matrices get sent off to different solvers and so on. We have a similar setup for our discretizations, because the discretizations end up looking like matrix equations. So here, if you focus on like A1 is an ultraspherical discretization. In this case for UXX, for the second derivative. B1 in our example was the identity, essentially. A2 was the identity, and B2 was the discretization that represents UYY plus 10,000 Y squared. Okay, so these are the kind of equations that we end up with, and we end up calling a bunch of different codes depending on that structure, and that's more efficient to solve it this way than solving it through Kronecker products, which you may have seen before. So typically in many textbooks on numerical solution of PDEs, when they get to 2D, they do Kronecker products and blow up the linear systems to be really large before solving them. Here, we always try to keep them small because blowing up for us is not an option, because n for us is huge. N can be in the thousands. So if we blow it up, we get that dimension gets squared. So we can't do that. So we often try to keep it in these matrix equation forms to solve them. So that's our algorithms. And in the end, we're calling adaptive code to decide on what our n actually should be in the end. So we do multiple solves on this. Okay, so here is a bunch of examples. So this is how we do all of these problems here. This is on a sphere. Okay, I've got this is an ultraspherical spectral method on the sphere, in the disk. This is me doing it. This is one of my students doing it in a cylinder. This is Adrienne Montanelli from Columbia doing it on a sphere for some pattern formation PDE. And so all of these guys in the end solve matrix equations and do that stuff. Okay. So once you have a 1D, any 1D method, you can get it to 2D by just thinking about separating the variables, low rank. Okay. Okay, and I don't know, everyone says I always solve simple PDEs, so I'm just trying to tell people that I don't. And so here's a more complicated PDE that we're doing with the active fluids to try to understand the flow of bacteria in a soccer ball. Okay, so this is like a generalized Navier-Stokes. One of the reasons that I really liked this PDE to play with is because it's very high order. So normal methods like finite element methods and finite difference methods suffer significantly because of the 6th order derivative. Whereas Fourier and ultraspherical spectral methods, they don't mind high derivatives are fine. Okay. Okay, so of course, you know, you try to publish papers, and sometimes you don't get back the kind of response that you like. Kind of at random, but anyway, so I submitted a paper, and this is the kind of thing I got back. I'd like to see this for 3D problems, multi-scale, multi-physics with uncertainty, perhaps start with the simulation of a wing attached to an Airbus in turbulence. Okay, so that was, I mean, I was solving things on a square, so it was a little bit of a jump.
That's tough.
That was, yeah. Yeah, so I didn't really know how to respond to that referee. So I thought, okay, let me try my best. Let's start walking towards more complicated problems then. So a lot of people think that you can only do things on simple geometries, tensor product domains, squares, disks. They're not surprised by those. But there's actually a construction that some people know in the field of orthogonal polynomials that allows you to do more complicated domains. And so like deltoids and triangles. So typically this is how it goes. If you have like your favorite polynomial basis in X, you could make that up to a square by just forming this product. And you got yourself a basis that works on a square. Koomwinder in his PhD thesis explained how you could make that more exotic to work on more different geometries. So here I'm actually showing you a set of functions that could be used, provided these PKs are nice, nice polynomials in 1D. The polynomial you're generating here will be relatively nice polynomials on a triangle. And so this allows us to, you know, form what we're thinking of as orthogonal polynomials on triangles, disks, deltoids, more exotic shapes. And as soon as we have that, we can build ourselves spectral methods that exploit these new bases. So so with Shianova and Jeffrey Vassell, you can see there's like a prox fun person, that's all Shianova, Cheb fun person, that's Townsend, and Jeffrey Vassell is a Daedalus person. So we were always interested in this. Got together and we were putting this together to get solvers on a triangle that are super fast. So this top example here is a Force-Helmholtz equation. There's about 1 million degrees of freedom being used to represent that solution to machine precision. And it's solved in like just over a second. Right? It's not that these are expensive methods. If you only want 3 digits, of course, you can rack down the discretization size. Okay, and we can even just start doing element methods. So once you have things in 1D, not only can you do tensor product domains, but anything that Koomwinder allows you to do. So a few more exotic domains there. But if you want to go truly exotic, right, any arbitrary geometry, you've got to get yourself into element methods. So at the moment, all spectral element methods, these are high order finite element methods, they have a terrible complexity in P, where P is the polynomial degree that you throw on each square. Typically it's P to the 6th divided by H squared, where H is the size of the element and P is the polynomial degrees you use on each element. So while it's pretty good in H, right? If I half H, I don't eat that much cost in my spectral element method. If I double P, I have a huge cost in doubling P. Hence why all finite element methods, this is from Spencer Sherwin, are for P less than or equal to 6. Right? Finite element methods always use low P because of this fact that doubling P increases their cost significantly. So I've been trying to come up with spectral methods that are more even in the complexity between P and H, because the ultraspherical spectral method has good complexity in P. Okay, so so we actually know once you can do 1D, you can do 2D through low rank. You can do more exotic domains through Koomwinder's construction. And then you can actually start piecing together elements too, triangles and squares, to do more complicated geometries. So here, if I want to solve on a square, I just made it simple, but I want to split it up into 4 squares. Then you could write down a linear system that discretizes any PDE on that square. It would have this kind of structure here, where it would be like 4 blocks corresponding to the discretization of the PDE on the 4 individual elements. And then you would have some dense things in the last column and some dense things in the last row, corresponding to continuity and continuity of derivative constraints that you're imposing on the solution across elements, because you want the solution to be continuous at least. So here, most people think about this in this hierarchical Poincaré Steklov scheme that I'm developing as solving for the interior nodes and then solving for the interface conditions, blue and red respectively. Now, Gunnar Martinson and Adriana Gilman have done a lot of work on this and have some very efficient solvers for these matrices that have this structure. In particular, they have basically a Gaussian elimination method that uses a pivoting strategy that's geometrically motivated, so that it doesn't densify the matrices, the matrix as it does the solver.
I have one question, Alex. Why the name? Why Poincaré in the name?
Yeah, because it's a very okay. So what happened was Gunnar Martinson and Adriana Gilman tried to publish a paper on it, calling it something like a hierarchical domain decomposition method, far more realistic. And a referee complained and complained and complained that Poincaré and Steklov had done some analysis on what's called Dirichlet-Neumann maps 100 years ago that would allow them to make this in a theoretical framework. So in the end, they gave up and they just said, okay, referee, you can have whatever name you want. So I think it's really just to please a referee as opposed to any intellectual. I think we're finding out that referees are sometimes random.
Yes. Okay.
Obviously, the referee loved Poincaré and Steklov. Okay. Anyway, that's what it's called. We have to live with that. Okay. Now, one issue that we have is that our methods that we're using always work in coefficient space. They were always working on the Fourier coefficients, the Chebyshev coefficients. And so we can't necessarily think about it as clearly as like interior nodes and interface nodes. So one reason we always work with coefficients is it's very easy to tell when you're working in coefficient space when you've resolved the function, because the coefficients decay to 0 as you resolve them. If you're working in value space, it's tricky to know when you've resolved the function. So anyway, sticking with coefficients, we have slightly adapted this method so that we can solve using the ultraspherical spectral method. So now here, these blocks down the diagonal, instead of being dense spectral collocation matrices, they're now sparse ultraspherical spectral matrices. So this has got an extra level of sparsity in it. And here we're just showing you a convergence plot as we change H and P. So we're just getting into this now, trying to build up to that Airbus wing as we try to go to 2D and 3D and develop spectral methods that can do very high P, which Spencer Sherwin would like if we can do that, particularly having a better complexity than what's out there already. So here I'm just showing an owl-shaped domain where we're partitioning in. Of course, once you can do squares, you can do quadrilaterals through just mapping, simple mappings. So here, and we can do also more general meshes with this using more exotic discretizations. Here I'm just showing a solution of a Helmholtz equation essentially on a Penrose shape. So I'm showing you like efficiency and like different types of meshes, different types of adaptivity, The owl-shaped domain here was done with different P's on each element. So we've got P and H refinement going on, which we hope to automate soon. And so this will be coming out with as a package, an add-on to Chebyshev. Okay. So I really like this. I was hoping to leave some time for lots of questions. So I really like this one line that's an opening book from Exploring ODEs, which says like, what happens if all you had to do is solve a DE was just to write it down. So all you had to do is write it down and you're done. And encapsulation would go and parse what you've written to a computer like Wolfram Alpha does, which we have. And then we discretize with our favorite method, or we actually have a cascade of different discretization schemes, depending on what geometry you're on, what kind of functions we see, and so on. And then we deliver back you an object which represents the solution. And at no point do you have to get your hands dirty and understand how we discretized and what algorithms we're going to use if you want to do subsequent computations with that function. So this is all built up with, carefully discretizing, making good algorithms, getting the adaptivity right, and then encapsulating that all up into software. And so coming in the very, very distant future is the Airbus wing example. Thanks to the NSF and the FACE Foundation. And thank you for having me.
Thank you very much.
So I've left maybe 10 minutes for questions. So I have lots of questions.
So are there any questions? So I am open to questions on the chat, or if you just want to start talking, you may just do it.
Hello, Alex. It's Olivier from Paris Nord and CRM. I have a question about the order of the operators, because at one moment for the Navier-Stokes equation, you had a 6th order operator.
Yes.
And do you keep in the approximation the same order of magnitude of the approximative operator? Do you have the same principal symbol or not? And if not, what are you doing to filter the high frequencies?
So yes, we do discretize this 6th order Laplacian and by changing basis. So we're walking up the ultraspherical hierarchy here as we discretize. Okay. We've got to go really far up because we've got 6 derivatives.
Okay.
And then what's your question? How do we do?
Because in fact, in this operator, it's of 6th order. So normally when you look at principal symbols, that's this one which is dominating normally.
Ah, okay, yes. So
how do you filter that?
Exactly. So actually these, okay, that's a great question. So these gammas have been set up very carefully. So that, okay, so here's a diffusive term. Here's a term that ends up being an activation term in certain Fourier modes. And this is a dampening term, right? By carefully selecting these gammas, what they've done in this PDE, the design of this PDE, is to get certain vortex sizes to be dominating. So if I look at this in Fourier space, and look at the ways these terms compete with each other, there's an annulus of Fourier modes in 2D that get excited. But then there's this advection term, which mixes things up, mixes low frequency with high frequency. And by carefully balancing these gammas with this advection term, you can get the PDE to be stable, at least observed to be stable. If you could prove it's actually stable, that might be close to the Clay prize of globally bounded smooth solutions to Navier-Stokes.
Okay, that's explained why, and that's a very nice thing to do. Thanks a lot.
So if you look at some of this original paper by Smomiak and Jorn Dunkel, they actually walk you through how to carefully pick these gammas. And at the end, they find a family of gammas, and then they go back to experiments and design the gammas to match empirical data from simulations of these bacteria that they're trying to model. Okay, good
Thank
question.
you.
Mm-hmm.
Okay, other questions? I guess there is one question here from again. Okay, no, it was another question. Okay, yeah, other questions or comments, sorry.
Yeah, I guess I've got a question, Stephen Watson from Glasgow in Scotland. I've got a question on this sixth order problem. So there's a range of higher order evolution equations, both in surface science, where you sort of, you reinterpret things. You don't have inertia, they're purely dissipative models.
Yeah,
right. You have similar higher order operators, fourth order, sometimes sixth order. I'm just wondering if your methods might be interesting to consider there as well. I mean, one main point here is that your highest order term, this choice of gamma 4, in some sense, the interesting limit for me mathematically, analytically, would be gamma 4 tending to 0. That would be a singular limit. So I guess there's two questions. One, of course, you can choose those coefficients to match empirical data. But then mathematically, it would be interesting to analyze the behavior as gamma 4 goes to 0.
Because of course, as gamma 4 goes to 0, this becomes an activation term. Because for large Fourier modes, this term is bigger than this term. This red term dominates.
So I'm making. So again, so there's analogous questions in and again in a surface science context where there is a meaningful singular limit.
Yeah.
Even though it's singular because the equation that it solves is not the one you get by setting gamma 4 equal to 0.
Okay, right.
There's an effective equation to be determined there. So I guess, two things. One, it'd be interesting to study that equation with your methods and that limit. And then the other would be perhaps to look at some of these surface science problems with the same sort of features of fourth order and sometimes sixth order problems.
Right, that's okay, great. I mean, if you would like to email me and we could set up
Sure.
a time to chat further, I would love to.
Glad to.
Okay, great. Thank you.
Okay, other questions or comments? I can see the list of participants here. Well, I guess I can take my turn now. So so at some point you at the very beginning of your talk, you were talking about the fact that when you differentiate Chebyshev polynomials, then that becomes a full dense lower triangle matrix.
Yes.
So then you use this ultraspherical and then you make it dense somehow. So but when you integrate Chebyshev polynomials, then you get something very nice. It's like a tridiagonal.
Yeah, you do.
And is there a reason why you're not using the tridiagonal structure? I mean, or you're not kind of rewriting your ODEs as integral equations as opposed to treating them directly with the ultraspherical?
Yeah, this is great. This is a great question. So this is very closely related to, well, this is integral reformulation.
Oh yeah.
And very closely related to integral preconditioning, where you can use those triangular matrices as preconditioners instead of. So integral reformulation is when you do the preconditioning essentially analytically. So okay, so this works absolutely fine in 1D. You can do this too. And this actually comes up also with exactly the same properties as this. It's a little harder to do in terms of if you have certain types of mixed derivatives here. I haven't got an example, but if I had, do you know Sturm-Liouville equations? The leading term there is ax u prime all prime. So there I've mixed in multiplication and derivatives. In those kind of things, it's hard to, at least automatically, pass the integral sign through automatically in software to get good discretizations for Sturm-Liouville problems. So there are certain corner cases where it's a little bit more awkward to discretize that in terms of automatic encapsulated software systems. But in the end, at least in 1D, it's very similar, except those methods do break down if you were trying to do things on a triangle, for example, because we don't have the same knowledge of how to do those integral preconditions, those integral reformulations, because now we have two derivatives. And so as you integrate an x, you've also integrated up the y one, and you don't want to. So so those techniques are really good in 1D.
Okay.
And I'm not sure they've been extended into triangles or higher dimensions.
Mm-hmm. Yeah, okay. I would think that, you know, in higher dimension, or let's say you can maybe write some Green's functions or to some integral free formulation of the PD and try to work from there. But
so some people, and some people, I mean, I have extra slides here, but okay. So some people down here, these Slonak, Strakos, Jordan Malek, these people use Rees operators to do exactly what you're talking about in higher dimensions as preconditioners, as the optimal preconditioners to use. But there's extra issues with that in terms of boundary conditions.
Okay.
So, but these are really good methods when you have simple boundary conditions. But when you have boundary conditions, for example, in here, this active fluids one, these are no slip boundary conditions. And I don't know, it's just a headache to try to understand how to discretize like that. So as I was saying, there are lots of methods out there that are similar in output in 1D, but the ultraspherical spectral method is as close as possible to the Fourier spectral method, in our minds at least. So that's what we were trying to achieve, to try to make a method look like Fourier spectral methods, because we might have a chance at generalizing it.
Mm-hmm. No, I like it. I was just curious. Yeah, no, it is very nice.
I give the perspective.
Yes.
Yeah. So yeah, our original paper has a very long discussion about all the connections to other methods out there.
Okay, thank you. Are there any other questions or comments? Well, I can maybe read. I don't know if you have access to the chat, Alex, but there is.
I've been looking at it as
okay, because you have now links from Stephen Watson following
yes.
his questions.
Yeah. Thank you.
So other questions or comments?
I guess I have one question, but it may not be in the right direction for what you're interested in. What about adaptivity with moving mesh, a notion that you actually adapt and move your domains?
Yeah, I've been thinking about
that. You also have in mind free boundary problems.
Yeah, I've been thinking about that a lot recently, because there's something that we found, but this is not published work, but I'm too excited, so I'll just tell you anyway. So I've been trying this spectral element method that we have on elements where the aspect ratio of the triangles are very poor. So very poor quality meshes. And we've been seeing that we can do extremely well on really poor quality meshes for some reason, as we rack up P for high order. We think it's something to do with extremely high order element methods. And we think this could be exciting for moving meshes, because you wouldn't have to reconstruct a mesh to keep the quality high. Mm-hmm. You could wait around, let your mesh get more and more entangled, and only have to regenerate when the approximation power starts dropping, which is typically way after the condition number of your finite element discretizations. So typically you regenerate, the cost for a moving mesh problem is all mesh generation. Mm-hmm. And you regenerate a mesh, not because it's a poor mesh in terms of approximation power, but because your discretizations are becoming so ill-conditioned. And here we're seeing, which we don't understand yet, that we're doing a really good job on poor quality meshes. So maybe that could actually be quite a computational saving for moving mesh problems, mm-hmm. if we had the right kind of setup. This is why
I guess, having said that, you're reminding me of things like, for example, Charlie Elliott's group. Uh-huh. They'll have done some very interesting work, which is basically, PDE on evolving surfaces. So maybe that's an interesting overlap point for you.
Okay,
that intersects. I know of that work because it intersects with my sort of surface science interest. The PDEs there, because you have free surfaces, and there's a PDE for the free surface, perhaps PDE itself on the free surface, but also coupled to a bulk. So you have all of that sort of structure there. The dimension of the bulk, the dimension of the interface, and perhaps a PDE itself on the moving interface. So I think Charlie Elliott's got quite a lot of activity in that direction with adaptivity. So
great.
You might find that interesting.
Okay, Charlie Elliott. Okay. I actually don't know that work, so that's a really good.
Yes, I mean he's been in that game for a long time. I mean, Zook is the person from Germany that he's done a lot of collaborative work with as the analytical person. But I mean, it's 10 years at least of kind of effort in that direction. So there's a rich sort of seam to dig into there.
Great, thank you.
Yeah, sure.
Thank you very much.
Okay. Well, I guess it is 5 p.m. right now, so maybe I can ask one last time if there are other questions, comments. So I don't see anyone being, showing it, unmuting himself. So I would say that, well, let's call it a day. Alex, thank you very much for accepting to give a talk. Very, very beautiful talk. I enjoyed it very much, I have to say. Lots of ideas for me, at least. Yeah, I'm also using Chebyshev a lot. Actually, one last question. So the approx fun that you mentioned from Julia,
Yes.
is this like taking ideas from Cheb fun, or it is like for very general?
Yeah, it's taking ideas from Cheb fun. It does. Yeah, it is. You could at least order 0 approximation is that approx fun is Cheb fun in Julia.
Okay.
But there are some. I mean, she and Olga would hate me saying that. So there are obviously extra features that approx fun can do that Cheb fun can't, and vice versa.
Okay.
It really has a different emphasis, but order 0 approximation.
Okay, fair enough. Okay, that's it. So yeah, I think that I mean, I hope that people liked it. I personally did a lot. Thanks for doing that for us. And well, yeah, I mean, perhaps people can just if they want to unmute and then say thank you or whatever, feel free. It's kind of the end.
Thank you, Alex.
Alex.
Thank you.
Very, very, okay. Good to see some human faces. I appreciate it.
Thank you.
Thank you.
Thank you.
Bye.
Okay, all right. So we'll stop the meeting now. So thanks, Alex, once again.
Thank you very much.